So, and I'm actually also at the same time I'm streaming it to internet just in case someone who wants to follow me online. I doubt it. But anyways, at the same time I also get a recording for the next year or for the students who are not here. As a matter of fact, one of our students I know is actually doing this one from Germany. So he's physically in Germany, and at least he claims that he's watching the videos and then does the exercises. Okay, so let me start with the show here. Don't mind me. I might actually use the whiteboard at some point, but okay, you just stay there if I can find my website. Not that one, is the 3003. All right, so that's the website we should be starting. Last time we had the signals and then systems. Now we should go through the responses. Okay, system responses. And as usual, I start with my nice slideshow here. Okay. And basically this is about system responses. Funny, this one doesn't work. Okay, first and most important response is the impulse response of the system. And it's simply the output of the system when there's an impulse signal is coming in. Do I have a picture on that one? Yes, I do. Excellent. So that's the definition. Nothing else. It's a definition, and basically quite easily to measure on digital world. On analog world, the real world, you would actually use step response for determining the system properties, just because the impulse is a little bit funny to make in continuous time. It has infinite value for a infinitely short period. All right. So, for example, on the 4-point running average filter, you just replace the input X with the delta. And that's your impulse response. Very simple thing. Yeah, and that's the nice graph of it. Okay. Basically, the systems are divided in two classes based on the impulse response. Finite impulse response and infinite impulse response systems. The finite means that it ends. The impulse response, when you have the impulse hitting the system, it actually at some point the signal dies out totally, completely. Okay, while the infinite impulse response systems, this signal is always there. A small amount of signal is there. Most of the natural systems are actually type infinite impulse response system. A simple RC filter, infinite. It has an exponential decay. Exponential decay of the signal after you hit it with the some change. Okay. So there's an example of 4-point running average filter. FR is FIR because of, well, you can see it from the impulse response. After the fourth time step, the signal of output dies totally. And then there's actually, I'm warning it already here, about the feedback and if the system is infinite or finite impulse response system. You must have a feedback to produce the infinite impulse response system. But it does not guarantee if you have a... Oh, okay. So we have a changing group here.
Yeah,
So,
change.
yeah. So after these lectures, the students can gather and start combining the information and, you know, got everything. Okay, welcome, welcome. Let me also take you on the tape. So this is the next group. So for you, for the informations, I'm also streaming this one on the internet and saving also on the YouTube. So you know now you're YouTube stars. Okay, so another Japanese group. I think there are still 2 groups coming, right?
Yeah, that's right.
Okay. Other 2 groups.
4 groups.
Okay, good. So yeah. So if the system has feedback, it does not guarantee that it will be infinite impulse response system. Okay, remember the last time we had this recursively implemented running average filter. It has a feedback, but it's still the same system with the same impulse response and with the 0 after fourth time step. Okay. Then about the transfer function and impulse response. This was already on the whiteboard last week. So if we have a LTI system with this funny sum of the inputs and outputs as the difference equation, then basically the transfer function h of z is simply z transform of the impulse response. Okay. And those students are such late. Okay, so impulse response. Still, system output for unit step. Unit not step. It's unit impulse input. Okay, and that actually means that if we have this running average filter again, then we just put the instead of x, we get the impulse response by putting delta instead of x, and then we do the z transform of that one, we'll find out, oh, that's quite simple to make this transfer function too. It's simply the z transform of those delayed weighted delta functions. Okay, then about zeros and poles and how actually we know from the zero pole plane or Argand's diagram if the system is a FIR or IIR. So that's quite simple. If you have any poles elsewhere than at the origin or cancelled pole on the unit circle, then you fundamentally have IIR system. So those 2 pictures on the top show the recursive version and non-recursive version of this the running average filter. It has a triple pole at the origin. On left hand side we have a pole on the unit circle, but it cancels out with that 0 at the same point. That was basically just to make the calculations faster. So we reduced one multiplication and addition there. All right, and why the lower graph, actually it's just an example that if you take these poles out of the origin, then it becomes actually a IIR system, since it has a, well, infinite impulse response. Duh. Okay. So step response is extremely important in analog world. In this digital world, it's not that useful anymore because everything can be derived from the impulse response, and that actually it's a little bit easier that way. Everything is a little bit easier. For example, the amplitude response. Well, because you take the impulse response, do the Z transform. That's directly your the transfer function, and when you evaluate the transfer function at unit circle, you get the amplitude and phase response. Okay. With the step response, you need to do some more calculus in order to do that. But anyways, 4-point running average step response. Yeah, that's how it goes. It's just a test. You use a step function as a test vector, run it through the system, and then you have the step response. Okay. Let's see what was my next slide. Oh shoot, that's ugly. Okay, arbitrary signal response. Well, arbitrary signal response basically means that you have a real signal. You just run it through the system. And those boxes, again, they should be sigmas. And as you can see, I didn't have any time to do it with those special characters last week either. Okay, maybe next week.
Yeah, is this basically just by running it as a feature that you just put something in?
Yeah, something else comes out. It's a let's see, it's a low pass filter. Any higher characters are dropped out. Okay, but anyways, arbitrary signal response can be calculated from the difference equation, although if you okay, now we are changing the students. Student groups, yep. Welcome. I'll pause a while. Alrighty then, we have the next group of visiting students. Actually, they are the guests of our student union here, so really student visitors. All right, but anyways, that's one example of basically if we had this 4-point running average filter, all of those three are the same system but 3 different implementation. So this is direct form, just plain calculus. Every single tab has their own multiplier, which is kind of stupid since you can just use one multiplier there. But on the other hand, doing this one a little bit different, you do a transform, and you know have one less. One less of the these additions, and that actually starts to make any bigger sense when you have, say, longer running averages. The system is still the same. Okay. Wow. This is ugly here, so I need to use whiteboard. All right, let's see. Excellent timing. Now I can use the whiteboard. All right, so frequency response. So we have the normal transfer function h of z of LTI system, linear time invariant system. I started like that, which is all simply the sum of the terms pk times z to minus k, and divided by a k z to minus k. Yes, please come in. There's some room on that corner or that corner. Yeah, or spread out. And this is the fourth group. Okay, welcome. So that's the transfer function from the last week. And yes, there's the multipliers of y are actually on denominator. And basically, if you calculate this one at z equals to ej omega, you will get the frequency response. So that's the frequency response, and z is just replaced by j omega. Bk times E2 minus jk omega. Same thing here, and there's absolutely no magic in here. It's just for calculus here. It's just complex numbers. And we have a complex number calculator called MATLAB. Does just perfectly those calculations. You don't need to care about it. You just need to find out in which points on the ej omega you want to evaluate this rational polynomial. Simple. And okay. I also write the other form. So this is also b0 divided by a0 times the product form. When you calculate the roots of the polynomial, you get the zeros and poles. E to j omega minus zk pi e to j omega minus pk. Those are the zeros and poles of the system. Okay, good. And your point where you evaluate is somewhere there. Omega, for example, on this angle, complex angle, or angle on the complex plane. Okay, let's put some physical meaning for that omega. So omega actually is. You should know that. You will have tests today on digital signal processing.
On this same topic.
Yeah.
It's supposed to be the energy in that focus, or time and dimensional energy, which you're trying to evaluate. If you have continuous functions, you have the energy from the history, energy from the future, and we try to evaluate what's the present effect on that all energy functions in your signal system.
Yeah. Yes. So that would be the transfer function actually, or this frequency response. How about this omega? Can you calculate the omega?
It's the mathematical perfect world. You can calculate in time instance. You can calculate whole frequency from 0 to infinity and minus infinity. But in real world, you only have the numbers you have crunch, and hopefully you have nothing as a noise. It will fuck up everything. So try to keep the in the analog world. Try to get the samples really well into your systems, and try to get rid of the noise before you get into trouble afterwards.
Yes, and you're in trouble.
Yes, I know.
So exact value of the omega. There's a formula how to calculate it.
Yeah,
2
it's
pi.
on the wall here. It's the
Okay.
amplitude and the angle.
Yeah. So 2 pi physical frequency over the sampling rate. Right. Something like that.
Normalized frequency.
Yeah. Normalized
I
frequency.
know he's really good on this.
Yes, I know. I have noticed. So, I know. I need a substitute teacher next week. Okay, but anyways, so there is actually a physical meaning for this angle. So when you are actually doing this calculation of the frequency response, this point here is at at the value or amplitude 1 on the signal, and with that physical frequency omega. Oh, actually omega, which is the angular frequency, and the normalized frequency, and that's actually 2 pi times physical frequency divided by the sampling rate, which basically means that on the upper half you have frequencies from 0 to pi, and pi is the same as sampling rate over 2, which is the Nyquist frequency. Okay. And then the lower part basically is the same thing from 0 to minus fs over 2. Okay. And with any physical frequency, this is actually just a mirror image of the other. And there's also a very good reason for it. You can actually put zeros and poles wherever you want. Start from that point. But in order to have real the system parameters, so it's basically from this one to that form, you really want to have these as real numbers, since the complex numbers, well, would just add some complexity to your calculations. You want to do the calculations as fast as possible. So basically, for that reason, these zeros and poles, what we have here, are always as complex conjugate pairs. Meaning, if there is a special point on angle, okay, omega 1, then there should be actually the same point at the same range at minus omega 1. Complex conjugate pairs. If you don't have, then you start having complex numbers here. So these system parameters must be kept real. These are always complex. Good. More stuff. So this slide is actually quite loaded with information without more explanations. So basically, this actually gives a complex spectrum, and it's a little bit hard to make any projections on complex numbers so that they would actually start making any sense. So for that reason, while this is the frequency response, we can simply do the amplitude or magnitude response by taking the magnitude of that. It's just that one, amplitude response. So absolute value of the frequency response. As then the other thing is very important, is the phase response, which tells you something about the time delay of the signal on some frequencies. So that's actually the phase response is the angle, complex angle of that such that your h, e, j, omega is simply, well, that's the magnitude times e to j omega. There. J of theta omega. So your phase response shows up in here. Okay, good. I have a nice picture of that one there. It doesn't have everything on it. All right, that's one example of an system, LTI system, amplitude or magnitude and phase response. And this is the 4-point running average filter. Okay, 4-point running average filter. There. So that's something you can actually calculate. Just put e to j omega wherever you have z on the transfer function. You will get cosine of omega minus I sine of omega. Okay, and then you take the magnitude of it and draw it in decibels. Of course, in decibels. This is a basically system attenuation as a function of frequency. The attenuation unit is decibels. This is engineering, not science. Okay. By the way, I will probably put another decibel calculation on some of the later exercises. There's still some mistakes on decibels on the first exercise. All right. So 4-point running average, and it has. Okay, let's see. I need to go to another whiteboard now. It has zeros on those places and poles at the origin, and then for some reason we have on this frequency response, or actually no, amplitude response. Does it say magnitude response? Yes, magnitude. Here's magnitude is 1, because 0 dB is 1. Okay. Then it actually dips down at the middle of this. I call it 0 since that's what it practically is. And then it also goes to 0 here. Why it's not going 0? Because, well, that's logarithmic scale. It goes quite deep when you take a logarithm of 0. So on linear scale, it would look like this. Okay, and that's a normalized frequency with the, well, it's multiplied by radians. So that one here is pi. This is pi over 2, and just for by chance, could this be actually pi over 2 and pi? Yes, they are.
Then it makes sense.
Yes, perfect, perfect. It makes a lot of sense. Well, this one actually, this one here. If you hit the 0, e to j times pi over 2, then you have the same spot as your 0 here. Okay, that's j omega going that way. On that spot, the numerator goes to 0. Poof! Exactly 0, not just close to 0, but really 0. So you have infinite attenuation on that point and that point. Wherever your the frequency hits the 0 point on unit circle, then you have a minimum and that minimum is 0. Okay, makes sense. So where do we need those poles then? Yep, that was the example. Wow, I have even a animation there. Maybe we should actually run that one too. Anyways, let's take another example. That's again, sorry about those missing.
Thank you very much.
Okay, you're welcome. Kiitos. So let's change that plot a little bit. I'll take one pole. Actually, let me take 2 of those poles, and just for fun, I will put them somewhere in here. This is not science. This is engineering. And yes, they are complex conjugate pairs, although they don't look like that. Maybe you should. When you look at this form, and especially, let me put the J omega equals that sum form B0 divided by A0, okay, and then we have the product of J omega minus ZK I e to J omega minus PK. All right, this here graphically is a distance between point on the unit circle to 0. It's a distance, yes, looks like a distance. And same thing here, this is distance from e to j omega to the pole. So if this one, the special points, actually give the minimum points here, how about the angles where we have the pole? That angle. Or that, omega p. P1. So actually, this one has a local minimum when you are at the same angle. So that distance here, e to j omega p1, then that distance is at the minimum. And when the denominator goes to minimum, what does it mean for the this function?
It has to go up.
It has to go up, yes. So basically on that angle, which is somewhere here, omega p1, on this case we get some amplification. And basically by calculating these kind of correctly, we can have a system with fairly flat, oops, that's not flat, fairly flat passband response compared to fairly good attenuation of the stop. Yeah, so that's fundamentally the idea on the IIR system or IIR filter design. You put the attenuation wherever you want. A lot of attenuation. You put the zeros on the unit circle. You know that that gives the 0 for the amplitude response, and then you put these poles close to unit circle. So take them out of the origin to provide some attenuation on the frequencies you want. Okay, let's see what happens to my animation if I click here. Ooh, yes, there's actually that dot going. And yeah, that's the 4-point running average again. And the calculations have been done. Those are the distances basically. Distances to those 3 origins, and multiplication of that one gives the whole thing. And when it starts, that point is as far as it can get on the unit circle from those origins. So that's the maximum. Okay. Does it make sense? Maybe. Okay. Good. Oh, great. Does it start it from the right place? Yes. There we are. Okay. So that's basically the same thing as I said there. So amplitude response local minimas are on the angles of zeros. So adding the zeros on the unit circle results in attenuation of signals. And then amplitude response has local maximas on the angles of poles. Adding pole node near to unit circle results in gain of signals. Okay. Now you can basically start adjusting the first filter. A couple of animations more. Yes, they are there. I'll just run them. Ooh, that's nice. That's us changing the zero location. So basically that gives the attenuation on the infinite attenuation on the certain angle. And now I'm adding some gain, moving the pole pair. And then I start moving those poles which are close to unit circle. So basically just having the nice kind of band pass filter, and then it starts it over again. The other one, oh, okay, so that's a flat response by setting those poles of the certain angles and ranges. Yep. Seeing is believing. Okay. How about the phase response then? The phase response, the magnitude response is kind of straightforward kind of thing. But then, what about the phase response? And then again, this Google slides are not the best ones for the mathematical equations. Okay, so phase response, that's a function inside of that box. Basically, it means that if you have a, okay, that's a little bit up on the picture. It's not quite, what it's supposed to be. Let me go to the whiteboard again. Ooh. All right. Just forgot to do that last time. Okay, the whiteboard. And okay, good. So we have a sinusoidal signal with amplitude A going into the system. Any system. Or this was discrete time system, but anyways. So what comes out is not that what I wrote there, but it's actually the original amplitude times the amplitude response, HEJ omega. Okay. times sine of omega t, that's on f, what's t? Omega t plus phase shift. All right, so phase shift actually shows you the how much the signal actually is delayed on the system. Okay. If we had a linear phase response, basically that would mean that that part is some constant times omega. Okay? Then this part actually sine omega t plus the phase shift would be sine of omega t, oops, that was small omega, plus k times omega. Wow, actually linear phase response means that we have omega times t plus k. So we have a constant time shift independent of the frequency, which is actually quite good. If you have, for example, this signal is a combination of two different frequencies and they are carrying this information simultaneously, then you want to actually have exactly the same amount of time shift when that signal goes through the system. Otherwise, you would have time shift between the information channels. So a good system actually, it may still have this filtering, but it still has the same time difference there.
So is it just that it takes, for example, half a second to go through the filter, but everything stays as
Yes.
it was and there's no
Yes.
extra distortion happening inside?
Exactly. So there's no phase distortion. Meaning, for example, for the pulse shape looks the same. So that kind of filters are required when you are actually taking any pulsed data, unless it's a common tradition to have nonlinear phase response, like in medical instrumentation, because the doctors know how to actually analyze the analog signals, not digitized signals, but analog signals with all kinds of filtering. So that, for that reason, actually, some of these medical instruments, they have the model of analog filter to basically simulate the behavior of an analog system. Just the doctor, when he sees a electrocardiogram, knows what it actually means. Those are very small signals, especially for when you are measuring anything from the body. Very small. And 30 years ago, 40 years ago, the signals were all analog. Now we can digitize it in very early state and would have much better filters in digital, but you know, let's have it as it was 40 years ago. Okay, good. So, but anyways, this one means practically that pulse shape remains same. After the filter. Okay. There are three kind of phase responses in reality. Yes, in reality, we also have zero phase response. Okay, how about if we have a system just like that and it's a nonlinear phase response? Can we do another system so that it reverses that effect? Yes, we can. Type by time, reversing the data. So we filter the same data with the same filter, but time reverse the data at the middle. So time reversing meaning minus on that one. Okay, then you get basically minus here, plus k, actually here, minus t plus k, and then you time reverse it again. Then you would have actually minus k and plus t, and everyone will be happy. So it's a plus minus k, meaning 0, meaning post-processing. Linear phase response, very important for the pulse shape remaining thing, especially on real-time systems. And non-linear phase response, that's the rest of the filters. Yeah, actually this k here or whatever, this actually it's linear phase response, meaning that that one here is actually d theta omega or d omega, and that's a constant. Yeah, times omega. That sounds like a first order approximation. But anyway, so if you take just this derivative of that phase shift as derivative of the omega, the frequency, then what then? That's actually called the group delay. Okay, and group delay is just a function that shows the time delay versus omega. All right, good. And there's a couple of things like linear phase response systems, group delay at passband. Well, that's the band that we are interested in, is constant, meaning the different frequencies will be delayed at the same time. And then linear phase responses of the signal. Zero phase response systems have zero time delay. Yes. Non-linear phase response systems will skew the signal somehow. Okay. And three examples. So input signal is a just square-shaped box. And for the linear phase response system, you basically have similar effects on the signal when it goes up or down. Actually, it's asymmetric. Linear phase response has asymmetric impulse response. Practically, that means that you could calculate it. It means FIR. Otherwise, you cannot make the symmetry over the 0 point. Okay, so only FIR systems can have exactly linear phase response. Then this non-linear phase response, as you can see, it's not symmetric anymore. The rising edge and the falling edge are more or less like mirror images. They are not symmetric anymore. They are not the same. It's also this reactive system. Okay. Then there's the zero phase response. By the way, there's also the real time delay now. So this linear phase response has quite a long time delay. Right. Why this nonlinear phase response system starts immediately when the signal starts. Zero phase response, on the other hand, that it's kind of non-causal, right? Because it shows that input signal, well, it starts at here, at point 21, but we have some signal already here. But it has zero phase delay, zero group delay. No time difference between the incoming signal and outcome system. Yeah, it's not real time. It's it's post-processed signal.
Are there any reasons why you would need that zero phase response? Because of course it takes some physical time.
Yeah, well, if you have yes.
I'm using the linear phase response
Yes.
and taking 20 indexes
Yeah.
off.
Astronomy.
Yeah.
The first applications were actually in astronomy, where you collect tons of the data, especially on radio astronomy. You just collect it, and then there was a team of 100 to 1,000 scientists who would try to find some correlation of the signal. There you can do whatever you please, since you have plenty of time. You will never find anything interesting. Okay, but engineering, usually you need to just, filter the signal and that's it. No post-processing. And yeah, well, of course, movies, that kind of things, they are all post-processed. So for the sound, you can do whatever you please. All right, more stuff. Spectrum analysis. Let me just check that I have the correct kind of view here. Yes, good. So spectrum analysis. So that was basically spectrum analysis of systems. And the only thing there is interested in spectrum analysis systems is the amplitude response and phase response. Amplitude response simply tells you the activation or magnification of a signal at a certain frequency, while the phase response tells you something about the signal delay. That's noon. Yeah. Our friendly neighbors just decided to. Okay. Maybe not. Yeah, power spectrum. Just a moment to check that batteries are okay. So power spectrum, when you're talking about the signal, then in order to do any filter, you need to know what kind of characteristics, spectral characteristics the signal actually has. And that you can get by a simple calculus called Fourier transformation. All right. So power spectrum of signal is simply Fourier transform of the signal multiplied by complex conjugate of the Fourier transform of the signal, or the Fourier transformation of the autocorrelation function. It's the same thing. And in discrete world, or digital world, discrete type signals, we have discrete Fourier transformation, which is mathematically beautiful. The sigmas and e to j omegas actually quite close to that. It's just also the pi and things like that there. Okay, but it's simply just a formula to calculate. And we have, since 70s, we have had the fast Fourier transformation. It's basically by Cooley and Tukey. I didn't know them. But anyways, they found out, okay, if you reorder some of these calculations on the discrete Fourier transformation, you can make it very fast. Meaning, normal discrete Fourier transformation takes in order of squared number of the samples to make. So n to power of 2 samples, the calculations to do the complete discrete Fourier transformation. Okay, then those two gentlemen actually found out, okay, there's a smarter way of doing it by basically splitting those sums of the multipliers to even and odd terms, and then change that odd term back to even term. Yeah, it's mathematically it's very beautiful how you do it basically, but anyways, it cuts the time to n log n number of calculations. So basically you're comparing parabola to something that goes like that, semi-linearly. Okay. And this is something like 32 or something like that. So even with a very small amount of samples, you better do it with the fast Fourier transformation. Okay, so practically on the MATLAB uses always fast Fourier transformation unless you want it to do something else. Okay. However, to get the most out of the fast Fourier transformation, you need to actually have the number of samples as a power of 2. 2 to the power of something samples, then you can get everything out of the fast Fourier transformation. Okay, so if you have smaller amount than, say, exactly, if you have 50,000 samples and want to do a Fourier transformation, if you cannot do that 64K samples, then you would be better off by adding 14,000 zeros on at the end of your record, compared to going to the discrete Fourier transformation. Okay. But anyways, 2 to the power of n. There is an example of spectrum analysis, and again we have power in decibels. Okay, and that's basically a window function times sine of 50 hertz. And why I have that window function there? Well, we have a discrete amount of data there. It's our sampling window. Mathematically, we have to take that one into account. Okay, so that actually shows the 50 hertz has a peak on it, and it's exactly at the 50 hertz just by accident. Okay, if we have 1,000 samples, actually you can only have the, well, let's see, 1,000 divided by, oh no, well, let's see. Is there something? Yeah, I did actually tell you something funny here. It's at 50 hertz because it has to be at 50 hertz, but how accurately it's at 50 hertz depends how big sample did you take. All right, I probably used here 1,024 samples, power of 2. Okay, and let's take here. So if that is back to this complex circle, that is sample rate over 2. Then the sample rate is here. It's the 2 pi is the sample rate. Wait a minute. I divided 1,000 samples per second in 1,024 points on unit circle. So basically I'm guessing that 50 hertz is just near to 50 hertz, not exactly the 50 hertz. Thousand samples per second divided by 1024, meaning that the spectral response is somewhat resolution is 0.9765625 hertz. Yes. And then a couple of other calculations here. 50 hertz divided by 1024 times something. No, what did I do? 1000 divided by 1024 equals that one times 50. Okay. So we have actually that peak is closer to 51 hertz than 50. Yeah. So there's 49 point. No. Let's see, wait a minute. No, it is quite close. The highest point is at 49.8 hertz, not 50, because that point is missing. Point is missing. So the Fourier. Let me take a couple of pictures here. Discrete Fourier transformation makes the mapping from discrete time signal to discrete frequency signal. Which means okay, so FFT. We have n samples at sampling rate fs. Okay, so basically if you take this kind of FFT, then you have n samples with the spacing in time space is that sampling time, so 1 over fs. That's the distance between subsequent samples, but when you do the Fourier transformation of the same signal, you get, okay, that's the frequency. You basically get delta f frequency, the resolution of sampling rate divided by the number of samples. Okay. And that up to the last point actually is sampling rate over 2. Okay, no, sampling rate over 2, yes. Sampling rate over 2. All right, good. So, and there you have the amplitude response only defined on those certain points. And, okay, and also these points here. So I already said you have n samples at sampling rate. You also have n samples also in FFT. This is only half of the signal. The rest of the signal is actually on the negative side. Why? Well, the complex circle tells you all. Remember, just like in the case of the systems, these are actually mirror images. The same thing also goes with the signals. So we have the negative frequencies right here and the positive frequencies right here from 0 to 5. This was Fs over 2, and which is also minus Fs over 2 right here. Okay. But anyways, when you are calculating the FFT, you will get the whole sample of the same amount of values on the output. You just need to make this kind of mapping to show the first half of it. So this is where we are really interested. Smiley face. Okay, good. Then a little bit different spectrum. I noticed some of you actually used a nice, I don't remember the URL anymore, but a nice service for repository for sounds. And it actually shows the spectrogram on the top of the sound sample when you download. That was cool. That was so cool. So actually, the spectrogram is very nice tool for anyone who is really interested about sounds.
Or radios.
Yeah, radio frequencies, whatever, any signals with that sound frequency information. Yeah, you can actually quite easily see the Morse code on. And also this, what is it? The old dial tones actually you can set see those on spectrograms then. But anyways, and dual tone multiple frequency. Yeah, that's the dial tones, DT. MF, good old times. I'm not missing them. All right, so basically spectrogram requires a little bit of explanations again. There we go. All right. So basically, a spectrum has a sample, n samples like that one, and it's kind of let me start from this one. So one single spectrum looks like this. Interesting, but how about if we want to know the time series, how this spectrum actually looks like, say, t0 at t equals 1. So maybe that frequency has changed. Okay. For that reason, the basically some people already on 50 started thinking of mechanism how to record spectrogram. Those are really nice piece of equipment. And the solution is quite simple because we have nice imaging systems nowadays. How about a picture which has time going from left to right? Why time goes from left to right? Why? Do you know why? Time Lord says so. It's a commonly time has said to go from left to right in Western world. Not in everywhere in the world, but in Western world, yes. Okay, that's the common way of doing it. From 0 to whatever the observers are. And then the another one which has a fixed thing on this spectrum is the frequency scale. So we can only show the signals from 0 to frequency scale. The Nyquist frequency, FSR2. So how about making this kind of picture? I need to add something to actually show where the signals are. So how about color coding them? Like some hot color code, or, well, I have black and white color code. 0 means white and high means black. So if I make something like that, that would be a chirp signal, meaning frequency started at that time, at that frequency, ended up at this frequency, at that time. Okay. Chirp. That's about chirp. And then how about the ambulance? Or it used to be like that, but now I don't hear them anymore. They're not so loud, so something like that. Okay, that's a spectrogram. And if I now draw a line like that here, you probably know how it would go. Yes. So it's a visualization of how spectrum is changing by time. And with the sounds, this is simple. There are also applications, as you said, on the radio. So dual tone multiple frequency means that you have those multiple frequencies somewhere in here. So for example, those frequencies would be the basebands for DTMF. So, and dual means that you have two different tones at the same time. So for example, this would mean something and that would mean some other key phrase. Okay. And then actually, all right, so that is, funny, usually American TV series where they have the high-tech instrument. Let me see the spectrum. Oh, there's someone saying something on the background. How we can actually find it? Well, they can, but anyways, they show that they can. Well, from the spectrum, you can start looking for the features that you are really interested about, and then you basically just get rid of the noise. So, if this was noise and that was noise, and you are interested only in DTMF signals, you would probably have 4 filters to filter only, pass only those 4 signals through the system and nothing else. Oh, you have nice signals there. Oh, wow. DTMF. What else do you find?
It's the modem signal.
Yes.
So all kind of stuff.
Excellent. So that's data.
Yeah.
So it looks like noise. Excellent. Yeah. So that's the spectrum. And that's my show. Good. Any questions? Can we go and eat? Yes. I'm planning to have a lunch break. I try to start at 1 o'clock. Yeah, but depending on the lines there, so if you want to. I'll see when about 90% are back, then I start. Okay.
8 kysymys sun tästä.